The water moving through your body right now is older than the sun it orbits. Not older than you. Older than the star at the center of our solar system. The water cushioning your brain, filling every cell, and carried in the slow rise and fall of your breath tonight began as ice in the cold dark of space, long before the sun first caught light. It is very likely the oldest thing you will ever hold, and you are holding it right now, simply by being alive. Tonight, we're going to explore the long 4.5 billion year history of the water inside your body. We will follow these molecules backward, out of your bloodstream and into the rivers and rain and ancient seas they passed through to reach you, back through the violent molten birth of the planet, and back further still, to a time before the sun existed at all. There is a genuine mystery at the center of this story, a question that took scientists the better part of a century to answer, and the answer turned out to be written into the chemistry of the water in your own veins. So how does water this old end up inside a body as new as yours? It helps to begin by noticing how much of you is water. An adult human body is somewhere between 55 and 60% water by mass. More than half of what you are resting here is water. It is in your blood, moving oxygen from your lungs to your fingertips. It fills the fluid that cushions your brain and spine. It sits inside every one of the trillions of cells that make up your muscles and your skin, holding their shape and carrying their chemistry. When you breathe in, water leaves your body as vapor on the way back out. You are, in a real and physical sense, a warm, moving arrangement of water, held together for a while in the shape of a person. And water is not only something you drink, it is the medium in which nearly all of your biology happens. Every reaction that keeps you alive, every signal your nerves send, every nutrient your blood delivers, takes place in water or is carried by it. Life on Earth did not simply arise near water. It arose within it, and it never left. Water is less a drink you take than the quiet canvas all of your living chemistry is painted upon. Without it, none of the rest of you would work for more than a few minutes. There is a gentle strangeness in it too. None of that water is truly yours. You did not make it, and you will not keep it. The water in you tonight is on temporary loan from the planet. It moved through clouds and oceans and the bodies of countless other living things long before it reached you. And when you are done with it, it will move on again, back into the rivers and the rain and the great shared reservoir of the earth. You are a brief stop on a journey that has been going on for billions of years, and that will keep going long after tonight. That is the thread we are going to follow. Not water in the abstract, but the specific water inside you right now, and the astonishing distance it traveled to get here. Because the strange truth is that Earth, by all the ordinary rules of how planets form, should have been born dry. It formed close to a young and violent sun, in a region of space far too hot for water to survive. By the physics of its own beginning, this should be a bare, rocky world, as parched as Mercury. And yet here you are, more than half water, breathing gently in the dark. That is worth sitting with for a moment. The most familiar substance in your body, the thing you take for granted every time you drink a glass of water, is also one of the oldest and most improbable travelers in the entire solar system. Its history reaches back past the oceans, past the dinosaurs, past the first rains that ever fell on this world, all the way to the space between the stars. Over the hours ahead, we are going to trace that history slowly, one careful step at a time, until it arrives right back here, inside you. There is nothing you need to do with any of this tonight, nothing to remember, nothing to hold on to. You can let it wash over you the way water does. So let your shoulders soften. Let the weight of the day settle out of your body and into the bed beneath you. Let your breathing slow, and let the room grow quiet and dark. We are in no hurry at all tonight, and it is perfectly fine if you drift off somewhere along the way. The water in you has waited 4.5 billion years. It can carry you gently through the rest. This is Cosmic Drift, where we tell the story of the cosmos softly, so you can rest. If you would like to keep drifting off to nights like this one, you are welcome to subscribe and settle in with us. And when you are ready, we will go back to the very beginning, to a young and molten Earth that had no business holding a single drop of water, and ask the first quiet question of the night. How does a planet born this close to the fire end up covered in ocean? 4.5 billion years ago, there was no Earth at all. No ground, no ocean, no sky. There was only a vast, slowly turning cloud of gas and dust, drifting in the dark between the stars, cold and quiet and enormous. This is where our story truly begins, not with a planet, but with a cloud. Something, perhaps the shockwave from a dying star nearby, gave that cloud a gentle push, and it began to collapse under its own gravity. As it fell inward, it started to spin, the way a figure skater spins faster when she pulls her arms in close. That spinning flattened the cloud into a wide, turning disk, with a dense, growing knot of matter at its center. The knot would become the sun. The flat disk around it, a swirling plate of gas and dust wider than our entire solar system is today, is what astronomers call the protoplanetary disk. Everything we know, every planet, every moon, every drop of water in your body tonight, came out of that disk. But the disk was not the same all the way through, and this is where the trouble for water begins. Near the center, close to the newborn sun, temperatures were tremendous. Friction and radiation kept the inner disk searingly hot, hot enough that rock itself could exist only as vapor. As the disk slowly cooled, the materials there condensed in a strict order set by temperature. Metals and rocky minerals, the substances that stay solid even when things are extremely hot, condense first and close in. Water, by comparison, is a delicate, easily boiled away substance. It is what scientists call a volatile, and in the heat of the inner disk, it could not become ice or gather into anything solid. It stayed as vapor, thin and scattered, unable to settle onto the growing rocky worlds. There was a line in the disk where this changed. Move far enough from the sun, out past where Mars orbits today, and into the region of the asteroid belt, and the temperature finally dropped low enough for water vapor to freeze into solid ice. Astronomers call this boundary the snow line, and in the early solar system it sat at roughly 2.7 times the distance from the Earth to the Sun. Inside the snow line, water stayed as vapor and drifted freely. Outside it, water froze onto dust grains as ice, and that ice became a building material, gathering into the cores of the giant outer planets and the icy bodies beyond. The snow line divided the young solar system into two very different territories, a warm, dry, rocky inner zone, and a cold, ice-rich outer one. Earth formed in the wrong zone for water, well inside the snow line, gathering itself from the same rocky, metal-rich material that condenses only where it is too warm for ice to survive. By the very nature of its ingredients, our planet was built dry. The early sun made things harder still. A young star does not shine steadily the way our sun does today. In its infancy, it passes through a turbulent, restless stage that astronomers call the T-Tauri phase, named after the young star where it was first studied. During this phase, the newborn sun blew out a fierce and gusty stellar wind, a steady gale of charged particles streaming outward in all directions. That wind swept through the inner disk like a great cosmic leaf blower, pushing the lightest, most easily moved material, including much of the leftover gas and water vapor, out and away from the inner solar system entirely. Whatever loose water might have lingered near the young Earth was being actively cleared out, blown toward the colder territory beyond the snow line. So picture the world forming under these conditions. The early Earth was not the calm blue planet we know. It was a ball of molten and half-molten rock, its surface a churning ocean of magma glowing at temperatures well above 1,000 degrees Celsius. It was still growing, still being struck again and again by the leftover rubble of the disk, and each impact added more heat. Any water that somehow reached that surface would have flashed instantly into vapor and been stripped away. There was no crust to hold a sea, no cool ground for rain to fall on, nothing but rock hot enough to flow like syrup. The newborn Earth was a place where liquid water had no way to survive. Add all of this together, and you arrive at a genuine puzzle, one that troubled scientists for decades. Earth formed in the hot, dry part of the disk. It was built from dry, rocky material. The young sun's wind was busy sweeping the last of the water away, and the planet's own surface was a sea of glowing magma that would have boiled off anything wet on contact. By every reasonable step of that reasoning, Earth should have ended up bone dry, cooling into a barren, rocky cinder, a larger cousin of Mercury, with no oceans, no rivers, no rain, and no life to wonder about any of it. And yet the planet you are lying on tonight is a water world. Oceans cover most of its surface. Water fills its air as cloud and vapor, carves its canyons, and moves through every living thing on it, including you. Somewhere between that molten, waterless beginning and the blue world of today, an enormous amount of water arrived and stayed and gathered into seas. That is the mystery this whole journey is built around. Not whether Earth has water, but how a planet that had every reason to be dry ended up so thoroughly, generously wet. It is a strange thing to sit with in the quiet of your room. The very conditions that made Earth a rocky planet in the first place, close to the warmth of the sun, are the same conditions that should have left it parched. The water in you exists in defiance of the place you were born, and to understand how that happened, it helps to look at a world that did not get so lucky. Because this story is not only about Earth. Right next door, one planet further out, there is a world that shows us the other path, the one Earth might so easily have taken. A world that seems to have started with water of its own, rivers and lakes and perhaps even seas, and then, over hundreds of millions of years, quietly lost almost all of it. That is where we are going next, to Mars, the world that had water and could not keep it. There is a canyon on Mars so long that, laid across our planet, it would stretch from Los Angeles to New York. It is called Valles Marineris, and it runs for roughly 4,000 kilometers across the Martian surface, in places 7 kilometers deep, far grander than anything on Earth. Its steep walls have been widened over eons by landslides and by the slow scouring of the wind. And though no liquid water runs through it today, the wider Martian landscape is threaded with the unmistakable shapes of water, dry riverbeds, branching channels that once carried runoff, the flat floors of basins that look, for all the world, like the beds of ancient lakes. For a long time, Mars was a genuine puzzle. Here was a cold, dry, rust-colored desert, its air so thin you could not survive an hour on its surface unprotected, and yet its face was carved with the signatures of flowing water, the same valleys and channels and sediment that water leaves behind here on Earth. The rocks were telling a story the present-day planet seemed to contradict. The rovers settled it. When NASA's Curiosity rover explored a crater called Gale, it found layered sediments of exactly the sort that settle out at the bottom of a standing lake, along with minerals that only form in the presence of liquid water over long stretches of time. Earlier rovers had already turned up the same kind of evidence elsewhere. The conclusion has become one of the more settled facts about our neighbor. Billions of years ago, Mars was a warmer, wetter world. Rivers ran across it. Lakes gathered in its low places. It may even have held shallow seas. Somewhere in its distant past, Mars was a planet where water flowed freely in the open air, under a sky thick enough to keep it liquid. And then, slowly and quietly, it lost almost all of it. To understand how a world loses an ocean, it helps to understand what holds an atmosphere in place, because the two are bound tightly together. A planet keeps its air by the strength of its gravity. The stronger the pull, the more firmly the planet grips the gas molecules at the top of its atmosphere, and the harder it is for them to drift away into space. Mars is a small world. Its surface gravity is only about 38% of Earth's. Standing there, you would weigh barely more than a third of what you weigh tonight, and that gentler grip made all the difference over the long ages of the solar system. There was a second loss, deeper and more decisive. Early in its history, Mars very likely had a churning molten core that generated a global magnetic field, an invisible shield wrapped around the whole planet, much like the one Earth still has today. That field mattered enormously because it deflected the solar wind, the same stream of charged particles from the sun we met in the last section. As long as the shield held, the solar wind was turned aside and the atmosphere was protected. But Mars is small, and small worlds cool quickly. Over time, its core cooled, and its inner dynamo faded, and the magnetic shield weakened and largely switched off. With the shield gone, the solar wind reached the top of the Martian atmosphere directly and began to strip it away, molecule by molecule, across hundreds of millions of years. As the atmosphere thinned, the planet grew colder, and here the loss began to feed on itself. A thick atmosphere, rich in carbon dioxide, traps warmth through the greenhouse effect and keeps a planet mild enough for liquid water. As Mars lost that atmosphere, it lost that warming blanket, and the surface temperature fell. Colder air holds less moisture, and colder ground freezes the water it holds. The planet slid into a kind of runaway refrigeration, each step of cooling locking away more water, and each loss of water and air deepening the cold. The rivers slowed and stopped, the lakes froze over, and, under the thinning air, their ice turned directly to vapor and drifted away. What water remained retreated underground, into vast reserves of subsurface permafrost, or froze into the polar caps, which to this day are made partly of ordinary water ice and partly of frozen carbon dioxide, what we would call dry ice. And so today Mars sits in a quiet, frozen kind of poverty. The pressure of its air is so low that liquid water cannot even exist on most of its surface. Set an open cup of water there, and it would not sit calmly. It would boil and freeze at nearly the same moment, torn between the two by the thinness of the air. The great canyon of Valles Marineris stands silent under a pale, dusty sky. The old riverbeds have not felt a current in something close to 4 billion years. The water is not entirely gone. It is locked in the ice caps and hidden in the frozen ground. But the living, flowing water that once shaped the surface is long finished, and the planet has become a monument to a wetter past it could not hold on to. It is worth pausing here, in the quiet, to feel how close this came to being our own story. Mars is not a strange or distant kind of world. It is a rocky planet, formed from much the same material as Earth, at much the same time, just one step further from the Sun. It had water. It very likely had the conditions for the beginnings of something interesting. And it lost all of that mainly because it was smaller. Its gravity was weaker, and its core cooled sooner and let its shield fall. Earth held on where Mars did not, and a good part of the reason is simply that Earth is larger and its magnetic shield still runs. That is a humbling thought to rest with. The water moving through your body tonight is here in part because our planet happened to be big enough and warm enough inside to keep it. Change a few of the numbers, make Earth a little smaller, or its core a little quicker to cool, and the water that fills your cells might have followed the Martian path, frozen into a polar cap, or blown away into the dark, on a world where no one was ever around to miss it. But Earth did hold on, and that only sharpens the question we have been circling since the beginning. Our planet not only kept its water, it somehow gained an ocean's worth of it, in defiance of a dry and molten birth. Before we can go looking for where all that water came from, we need a way to tell one kind of water from another, a way to read the history of a water molecule from the water itself. And it turns out that every drop of water carries a quiet signature written into its atoms, a fingerprint of where and when it was born. That fingerprint is where we are going next. All water looks the same. Pour a glass from the tap, scoop a handful from a mountain stream, melt a piece of glacier ice that has sat frozen for 10,000 years, and you could not tell them apart by looking. They are all clear, all wet, all made of the same simple molecule. And yet, on a level far too small to see, each of those waters carries a quiet record of where it came from. To read that record, we need to look closer than the drop, closer than the molecule, all the way down to the individual atoms that make it up. Water is one of the simplest molecules there is. 2 atoms of hydrogen bound to 1 atom of oxygen. That is the whole recipe, the reason we write it as H2O. And of the 2 ingredients, it is the hydrogen that holds the secret we are after. Hydrogen is the smallest and simplest atom in the universe. A single proton at its center with a single electron circling around it. Nothing else. It was the very first kind of atom to form after the birth of the cosmos, and it is still by far the most common. Almost every hydrogen atom in existence, including nearly all of the ones inside the water in your body, is this plain, light version, 1 proton and 1 electron and nothing more. But not quite all of them. A small number of hydrogen atoms are built slightly differently. They still have their single proton and their single electron, so they are still, chemically, hydrogen. But tucked into the center, alongside the proton, they carry 1 extra particle, a neutron. That neutron adds no electric charge, so it does not change how the atom bonds or behaves in water. What it adds is weight. A neutron weighs about as much as a proton. So this heavier version of hydrogen weighs roughly twice as much as the ordinary kind. We give it its own name. We call it deuterium. It helps to think of hydrogen and deuterium as twins. They look almost identical. They act almost identical. And in a glass of water, they mix together freely and do the same chemical work. The only difference is that one twin is carrying a small, quiet extra weight, the other is not. Ordinary hydrogen is the light twin, quick and nimble. Deuterium is the heavier twin, doing everything the same, just carrying a little more with it wherever it goes. Scientists call these 2 versions isotopes of hydrogen, different weights of the same element. When deuterium takes the place of ordinary hydrogen in a water molecule, you get what is sometimes called heavy water. It looks like ordinary water, it flows like ordinary water, it freezes and boils at very nearly the same temperatures, but it is measurably heavier and slightly more sluggish in the delicate business of evaporating and condensing. And that small difference in behavior is exactly what makes water molecules keep a memory of their birthplace. Here is why that matters. Because the heavy twin is a little slower to evaporate and a little quicker to settle, the ratio of deuterium to ordinary hydrogen in any batch of water depends on the conditions where that water formed. How hot or cold it was, how far it was from the sun, whether it condensed in the warm inner solar system or froze in the deep cold beyond the planets. Colder, more distant water tends to end up carrying more of the heavy twin. Warmer, closer water tends to carry less. The balance between the two, the deuterium to hydrogen ratio, becomes a kind of thermal fingerprint, a permanent record of the temperature and the place where those molecules first came together. Water does not forget where it was born. This is the tool that turns a vague question into a solvable one. We wanted to know where Earth's water came from. Now we have a way to ask it precisely. We can measure the deuterium to hydrogen ratio of the oceans, and we can measure the same ratio in any suspect, any comet or asteroid or grain of space dust we can reach, and see whether the fingerprints match. So what is Earth's fingerprint? Scientists have measured it very carefully, using ocean water as the reference standard. The benchmark even has a formal name, the Vienna Standard Mean Ocean Water, which is simply a precisely defined sample that represents the average composition of the world's oceans. In that standard, deuterium makes up about 156 parts per million of all the hydrogen present. Put more plainly, for roughly every 6,420 ordinary hydrogen atoms in Earth's seawater, there is just one heavier atom of deuterium. It is a tiny fraction, a single heavy twin lost in a crowd of thousands. But it is a remarkably steady fraction, consistent across the oceans, and that steadiness is what makes it useful. It is a number the Earth's water has carried for billions of years, and any true source of that water should carry very nearly the same number. That one figure, one deuterium for every 6,420 hydrogen atoms, is the fingerprint at the center of this whole story. Hold on to it loosely. You do not need to memorize it. Just carry the idea of it, the sense that Earth's oceans have a specific chemical signature, as exact and identifying as a fingerprint pressed onto glass. And with that, the shape of the rest of the night comes into focus. From here on, this becomes a kind of quiet detective story, unfolding at the pace of the cosmos. Out there in the solar system are several possible sources for Earth's water. Comets, made largely of ice. Asteroids, which carry water locked inside their rock. The sun's own wind. Even ice older than the sun itself. Each of them is a suspect, and each carries its own fingerprint, its own deuterium to hydrogen ratio, set by the conditions where it formed. Our task, over the coming sections, is to travel out to these suspects one by one, measure their fingerprints, and compare each against the signature of our oceans. Some will not match at all, and we will set them gently aside. Others will come surprisingly close, and in the end, more than one of them will turn out to have left its mark inside you. There is something deeply satisfying in this, the way a real method quietly clicks into place. For most of human history, the origin of the oceans was simply a mystery, a thing to wonder about with no way to test. Now, because a small fraction of hydrogen atoms happen to carry an extra neutron, And because that extra weight leaves a trace, we have a way to actually ask the water where it has been, and to get an answer we can check. The whole vast question of where Earth's water came from turns on a difference so small it took some of the most sensitive instruments ever built to measure it. So we have our fingerprint, one heavy atom in every 6,420, and our list of suspects waiting out in the dark. The natural place to begin is not with something exotic and far away, but with something that once fell out of the sky and landed, quietly, in a field. On an ordinary Sunday morning, in a small town in Australia, a stone arrived from space carrying water inside it. And when its fingerprint was finally measured, it looked a great deal like our own. It was the morning of the 28th of September 1969, and the town of Murchison, in the state of Victoria in southeastern Australia, was going quietly about its Sunday. Murchison is a small farming community, the kind of place where the loudest thing on a weekend morning is usually the wind moving through the paddocks. Then, a little before 11 o'clock, a bright fireball crossed the sky, trailing smoke, and broke apart with a rolling sound that people heard for miles. In the minutes and hours that followed, fragments of dark stone came down across the fields and roads around the town. Local residents went out and picked them up, some still faintly warm, and noticed something curious. Many of the pieces gave off a distinct smell, a whiff of something almost like methylated spirits or tar. These plain-looking dark rocks, scattered across ordinary Australian farmland, smelled faintly of chemistry. Altogether, people recovered something on the order of 100 kilograms of material, in pieces ranging from small chips to stones you could hold in two hands. It was a generous fall, and because so much was collected so soon after it landed, and by so many careful hands, the Murchison meteorite became one of the most studied objects ever to arrive from space. More than half a century later, laboratories around the world are still learning from it. What made it so valuable was its type. Murchison is what scientists call a carbonaceous chondrite, and to understand why that matters, it helps to know what those two words mean. Chondrites are the oldest and most primitive meteorites we have. They are not fragments of a planet or a moon that melted and reformed. They are, in a real sense, leftovers, clumps of the original material of the solar system that came together in the first few million years and were never afterward heated enough to melt and erase their history. When you hold a chondrite, you are holding matter that has scarcely changed since before the Earth finished forming. The word carbonaceous simply means it is rich in carbon, and in the compounds carbon builds. These are the dark, primitive, carbon-bearing stones, the closest thing we have to a sample of the raw ingredients the solar system was made from. And locked inside that ancient, unmelted rock was water. Not water in pools or droplets. You could not wring a carbonaceous chondrite out like a sponge. The water in Murchison is bound chemically into the structure of its minerals. Long ago, on whatever parent body this stone broke off from, liquid water once seeped through the rock and reacted with it, forming clay minerals, the same broad family that makes up ordinary clay here on Earth. Those clays hold water within their crystal structure, woven into the mineral itself at the atomic level. When scientists measured how much water was held this way in carbonaceous chondrites like Murchison, they found it could amount to as much as 10 to 12% of the stone's weight. More than a tenth of these dark meteorites, by mass, is water that has been carried through space, locked safely inside rock, since close to the dawn of the solar system. That alone would have made Murchison remarkable. But there was more. When chemists examined the stone closely, they found it was not only carrying water. It was carrying an entire suite of organic molecules, the carbon-based compounds that life on Earth is built from, including amino acids, the small building blocks that link together to form proteins. Dozens of different amino acids were identified in Murchison, some familiar from living things on Earth, others not found in earthly biology at all. The presence of amino acids in a meteorite raised an obvious and careful question. Might these simply be contamination, ordinary earthly molecules that soaked into the stone after it landed in a field? Scientists had a clever way to check, and it turns on a subtle property of these molecules. Many organic molecules, amino acids among them, can exist in two mirror image forms, a left-handed version and a right-handed version, like a left and a right glove. Life on Earth is famously lopsided about this. Living things build their proteins almost entirely from the left-handed form. Molecules made by ordinary chemistry, with no life involved, tend to come out in a roughly even mix of both hands. And when the amino acids in Murchison were examined, they showed a much more balanced mixture of left and right than earthly life produces. That balance was the tell. It meant these molecules had not been made by living things. They had been assembled by plain chemistry, out in space, before the stone ever reached us. So here was a dark, unassuming rock that had fallen into a quiet farming town, and inside it was a small chemical portrait of the early solar system. Water woven into its clays, the organic building blocks of life, made without any life to make them. It was a reminder that the ingredients for a living, watery world were not rare or precious things that had to be invented on Earth. They were riding along inside ordinary space rocks, drifting through the solar system, waiting to be delivered wherever such stones happened to fall. And then came the measurement that connects Murchison directly to our story. Remember the fingerprint from the last section, the deuterium to hydrogen ratio. One heavy hydrogen atom for roughly every 6,420 ordinary ones in Earth's oceans. Scientists took the water-bound inside carbonaceous chondrites like Murchison and measured its deuterium to hydrogen ratio, and the result was striking in its ordinariness. The water in these ancient stones carried a fingerprint remarkably close to the water in our seas. Not wildly heavy, not strangely light, but sitting right in the neighborhood of Earth's own oceans. Sit with that for a moment, quietly. A stone that formed near the beginning of the solar system, that spent billions of years drifting in cold and dark, that fell out of the sky onto a Sunday morning field in Australia, was carrying water whose atomic signature looks like a close match for the water in your own body tonight. The ocean's fingerprint, or something very near it, had just turned up inside a rock from space. This was the first strong clue in the case. Carbonaceous chondrites, these dark, water-bearing, organic-rich stones, looked like exactly the kind of source we were hunting for. They carried water. They carried it in enormous, planet-worthy proportions if you gathered enough of them. And their water matched. For the first time, we had a real suspect whose fingerprint fit. But a single stone, however suggestive, is not an ocean. Murchison weighed 100 kilograms. Earth's oceans are something else entirely, a quantity of water so vast it is genuinely difficult to hold in the mind. Before we can seriously ask whether stones like this filled the seas, we need to reckon honestly with the scale of what we are trying to explain. We need to sit for a while with the sheer, staggering size of an ocean and ask whether a slow rain of small stones could ever, over enough time, add up to that much water. That is where we turn next. Let us slow down here and simply look at the water. Most of the time, we meet water in small amounts. A glass on the nightstand, a cup of tea, the rain against a window. Even a lake or a river, large as it seems when you stand beside it, is a quantity the mind can more or less hold. But the oceans are something else. They cover roughly 70% of the surface of the planet, wrapping most of the world in a single connected sheet of water. When you look at a photograph of the Earth from space, that deep calm blue is the first thing you see. It is the defining feature of our world, the thing that makes it recognizable from millions of miles away. Now try to gather all of it into a single number. If you took every ocean, every sea, all the water in all the great basins of the world and measured its volume, you would arrive at something close to 1.335 billion cubic kilometers of water. It is worth letting that phrase settle, because the words go by faster than the meaning. 1 billion cubic kilometers. Each single cubic kilometer is a block of water 1 kilometer long, 1 kilometer wide, and 1 kilometer deep. Already far more water than most of us will see in a lifetime. And there are more than 1 billion of them, gathered together into the seas of one small planet. There is a gentle way to picture it that scientists sometimes use. Imagine reaching down and lifting all of the ocean off the Earth, every drop, and rolling it up into a single sphere floating in space beside the planet. You might expect that sphere to be nearly as large as the Earth itself. It is not. Gathered into a ball, all the water of all the oceans would form a sphere only a few hundred kilometers across, small enough to sit as a modest blue bead beside the great curve of the continents. This is one of the quiet surprises of our world. The oceans feel limitless when you stand at the shore, and yet the total amount of water is, in planetary terms, a thin and precious film, a small blue drop resting on a large ball of rock. Precious, and still, by any human measure, almost unimaginably vast. That is the amount of water we are trying to explain. Not a glass, not a lake, but well over 1 billion cubic kilometers of it, sitting on a planet that we said, only a few sections ago, had no business holding a single drop. Somehow, that entire blue film arrived on a world that was born dry and molten, across the long, slow ages of the early solar system. And this is where the scale becomes a genuine problem, not just a wonder. In the last section, we met Murchison, a water-bearing stone from space that weighed about 100 kilograms and matched the ocean's fingerprint. That match was thrilling, but 100 kilograms of rock, even if 1/10 of it were water, holds only a few buckets worth. Set that beside 1 billion cubic kilometers, and the gap is almost dizzying. The suspect fits the fingerprint beautifully. The trouble is arithmetic. How could a slow arrival of comparatively small stones, most no larger than a hill, ever add up to fill the ocean basins of an entire world? The answer lies in the one resource the early solar system had in enormous supply, and that we so easily forget when we think in human timescales. Time. Deep, patient, almost endless stretches of it. The delivery of Earth's water was not a single grand event, not one great flood poured out all at once. It was a slow accumulation, spread across many millions of years. Picture not a storm but a rain, an extraordinarily gentle and unhurried rain of stones falling onto the young Earth across a span of time so long it barely makes sense to us. One water-bearing rock arriving, then another, each adding its small share of water to the growing world. No single impact mattered very much. But given enough impacts and enough time, the small shares added up. Drop by drop, stone by stone, across an ocean of years, the basins slowly filled. There is something quietly moving in that image when you sit with it in the dark. The seas that cover most of our planet, the water that carved the coastlines and fills the clouds and moves through every living thing, did not come from one dramatic moment. They gathered, patiently, from countless small arrivals, over a stretch of time longer than the mind can really hold. The ocean is, in a sense, an act of deep patience, an enormous total assembled from a vast number of tiny contributions, none of them urgent, all of them adding up. And the same is true, in the end, of the water in you. The small amount inside your body tonight is a portion of that great slowly gathered total, drawn from a reservoir that took the early solar system millions of years to fill. You are carrying a few handfuls of the ocean, and the ocean itself was carried here a little at a time, over almost unthinkable stretches of time. So the scale, at first a problem, becomes part of the answer. The oceans are far too large to have arrived all at once, but they had all the time in the world to arrive slowly. Which brings us back to the question of exactly what was doing the delivering. We have one suspect already, the dark carbonaceous stones like Murchison, and their fingerprint fits. But before we accept them, honest detective work means examining the other obvious candidate first, the one most people would name if you asked them where Earth's water came from. Not rock, but ice. Great mountains of ice, sailing in from the outer dark, with glowing tails stretched across the sky. It is time to consider the comets. If you had asked an astronomer a few generations ago where Earth's water came from, many would have pointed without hesitation to the comets. And it is easy to see why. Comets are, in the most literal sense, mountains of ice. They are the most water-rich objects we know of in the whole solar system. Bring one close to the sun, and it does exactly what you would expect an icy body to do. It warms, its ice turns to vapor, and it unfurls that long, glowing tail across the sky, a tail made in large part of water. When you are looking for the source of an ocean, an object that is mostly frozen water seems like the obvious place to start. For a long time, we did not really know what a comet was made of. The person who gave us our modern picture was an American astronomer named Fred Whipple, who in 1950 proposed what became known as the dirty snowball model. Before Whipple, some thought comets might be loose clouds of dust and gravel, flying sandbanks with no solid heart. Whipple argued instead that a comet has a genuine solid nucleus, a single body made of ices, water ice chief among them, mixed together with dust and darker material. A dirty snowball, in other words, or perhaps more accurately, an icy dirt ball, a few kilometers across, holding together as it loops through the solar system. When it nears the sun and its ices begin to vaporize, that is what forms the glowing head and the streaming tail. Whipple's picture turned out to be essentially right, and it made comets look, for decades, like the leading candidate for delivering Earth's water. They had the water. They struck the early Earth. The case seemed almost to make itself. But we have a way now to test that case rather than simply assume it. We have the fingerprint. If comets delivered Earth's oceans, then the water in comets should carry the same deuterium to hydrogen ratio as the water in our seas, that signature of one heavy hydrogen atom for roughly every 6,420 ordinary ones. The only way to truly check was to go to a comet and measure its water directly. And in the 21st century, we did exactly that. The mission was called Rosetta, and it was one of the most ambitious the European Space Agency has ever flown. Launched in 2004, Rosetta spent 10 years crossing the solar system to reach a comet with a long and much abbreviated name, Comet 67P Churyumov-Gerasimenko, usually shortened simply to 67P. In 2014, Rosetta did something no spacecraft had done before. It did not merely fly past its comet in a rushed few hours. It slowed down and settled into orbit around 67P, becoming a lasting companion to the comet as it traveled, escorting it in toward the Sun and watching up close as its ices began to warm and vent into space. That close, patient vantage was the whole point. As 67P neared the Sun, jets of gas and vapor lifted off its surface, including water vapor rising directly from the comet's ices. Rosetta carried an instrument called Rosina, a highly sensitive detector built to sample that venting gas and measure its exact composition, atom by atom. This was the moment the comet theory had been waiting decades for. For the first time, a spacecraft was tasting the water of a comet directly and reading its fingerprint on the spot. The result did not match. It did not match by a little either. The water venting from comet 67P carried a deuterium to hydrogen ratio roughly 3 times higher than the water in Earth's oceans, 3 times as much of the heavy hydrogen twin. In the language of the fingerprint, this was not a smudged or borderline result that might be argued either way. It was a clear mismatch. Whatever filled Earth's seas, the water of 67P was far too heavy to have been the main source. This particular comet, at least, was carrying a signature that plainly did not belong to our oceans, and 67P was not entirely alone in this. When astronomers gathered the comet measurements they had, most of the comets studied, especially those coming in from the most distant, coldest reaches of the solar system, showed the same tendency toward water that was too heavy, too rich in deuterium, to match the Earth. There is a clean physical reason for this, and it takes us right back to the fingerprint's meaning. Deuterium-rich water is the signature of water that formed in extreme cold, far from the Sun. Comets are creatures of the deep outer solar system and beyond, born and stored in the coldest regions there are. So it makes sense that their water would carry a heavier fingerprint than water that formed nearer in. The comet's own history is written into their ice, and that history is one of profound cold, not of the warmer inner solar system where Earth was made. Calmly, and on solid evidence, we can set the leading suspect aside. Not entirely, and not with drama, because the picture still has some nuance. A few comets have been measured with ratios closer to Earth's, and comets almost certainly delivered some small share of our water, along with everything else that struck the early planet. But as the main source, the great reservoir that filled the oceans, the comets do not fit. The most obvious candidate, the one nearly everyone would have named, turns out not to be the answer. This is how a careful investigation actually works. You take your strongest first guess, you find a way to test it against the evidence, and when the evidence says no, you follow it, even away from the comfortable answer. There is something quietly satisfying in that. For all their beauty, for all the drama of their glowing tails, the comets did not fill our seas. And ruling them out is not a loss. It is progress. It narrows the search. It tells us to turn our attention away from the spectacular ice of the outer dark and back toward the humbler, darker candidate we already met, the water-bearing rocks, whose fingerprint sat so much closer to home. But before we follow the trail to those rocks, and to the extraordinary journeys that flung them toward Earth, there is a chapter in the planet's history we need to understand. The story of how and when all these bodies came raining down on the young world. To read that story, we have to look not at the Earth, whose surface has been endlessly reworked and erased, but at the still, patient face of the Moon, where the record of that ancient bombardment was written, and then, remarkably, kept. Look up at the full moon on a clear night and let your eyes rest on it for a while. you will notice that it is not one even shade of grey. There are darker, smoother regions, the wide plains the early astronomers mistook for seas and named the Maria, the Latin word for seas. And there are lighter, rougher regions surrounding them, the lunar highlands. If you could look closer, through even a modest telescope, those bright highlands would resolve into something remarkable. They are covered, almost saturated, with craters. Craters upon craters, overlapping and interrupting one another, layered so densely that new impacts have landed on the rims of old ones, going back and back into a scarred and complicated past. Those craters are a record. Every one of them is the frozen mark of something striking the moon long ago. And here is what makes the moon so valuable to us. The moon is a quiet, geologically still world. It has no rain to wear its surface down, no rivers to carve it, no drifting continents to fold it under, no thick atmosphere to soften an incoming stone into a shooting star. On Earth, the marks of ancient impacts have almost all been erased. Wind and water and the slow churning of the planet's crust have wiped the early record nearly clean. But the moon has kept its scars. Its cratered highlands are a preserved archive, an ancient page that records the storm of debris the young inner solar system endured, a page the Earth once shared and long ago lost. For a long time, though, the craters could only tell us so much. We could see them and count them, and see that the highlands were older and more battered than the smooth, dark plains. But a crater by itself does not carry a date. We could read the story of the bombardment in outline, but not in time. That changed when human beings walked on the moon and brought pieces of it home. Between 1969 and 1972, the Apollo missions returned to Earth carrying lunar rocks and soil, samples gathered by astronauts from several different landing sites. Back in the laboratory, scientists could do something with those rocks that no telescope could do from afar. They could date them. The method is called radiometric dating, and it relies on a beautifully steady piece of physics. Certain kinds of atoms are radioactive, meaning they slowly and predictably transform into other kinds of atoms over time, at a rate that never changes. By measuring how far that transformation has progressed inside a mineral, scientists can read how long ago that mineral last formed, or was last melted, like reading a clock that has been ticking, atom by atom, since the rock cooled. It is the same fundamental technique that lets us say the solar system itself is about 4.5 billion years old. When the Apollo rocks were dated, something unexpected turned up. A striking number of them, especially samples associated with the great impact basins, seemed to cluster around a similar age, somewhere near 3.9 billion years ago. To many scientists at the time, that clustering suggested something specific and dramatic. It looked as though the inner solar system had gone through a sudden, intense spike of impacts around that time. A relatively brief and violent episode in which the moon and the Earth beside it were pelted far more heavily than before or after. This proposed episode was given a name that has stuck ever since, the Late Heavy Bombardment, and it fit rather neatly into the water story, because a concentrated rain of impacts around that period could have been a major delivery of water-bearing bodies to the young, cooling Earth. For years, the Late Heavy Bombardment as a sudden cataclysm was widely accepted, taught as a chapter of solar system history. But this is a good place to slow down and be honest about how science actually behaves, because the picture has grown considerably less certain in recent times. The trouble is that the evidence for a sharp spike rests heavily on those Apollo samples, and the samples came from a limited set of places, all relatively close together on the near side of the moon. there is a real possibility that many of them were thrown out by one or two enormous impacts, so that the ages cluster not because impacts across the whole moon peaked at once, but because a few great collisions scattered their debris widely and stamped a similar date onto rocks that were really recording the same handful of events. In more recent years, many scientists have come to favor a gentler and, in some ways, less tidy picture. Rather than a calm early solar system suddenly disrupted by a burst of impacts, they see a long, steadily declining rain of debris, heaviest at the very beginning when leftover rubble was everywhere, and tapering off gradually across hundreds of millions of years. In this view, there was no dramatic spike at 3.9 billion years. There was simply a great deal of bombardment early on, thinning slowly and unevenly over time. Which of these pictures is right is still an open question, actively debated among the people who study it most closely. And rather than being a frustration, that unsettledness is worth appreciating for what it is. It is what honest science looks like from the inside. We have real evidence, the craters and the dated rocks. We have more than one reasonable way to read that evidence, and we hold our conclusions loosely, revising them as new samples and new analyses come in. A confident, tidy story that turns out to be wrong serves no one. A careful, still open story that keeps faith with the evidence is worth far more. What both pictures agree on, and what matters most for our purposes, is this. The early inner solar system was a place of frequent impacts, far more so than the calm sky we know today. The young Earth, still cooling, was struck again and again by the leftover bodies of the disk, among them the dark water-bearing rocks we have been tracking. Whether that delivery came as a single late storm or as a long fading rain, the essential fact holds. There was a long era in which material from across the solar system came down onto the Earth, and a great deal of the water in our oceans and in you arrived during it. That still leaves a deeper question, one the craters alone cannot answer. What was sending all this material inward in the first place? A steady rain of stones does not simply happen. Something had to disturb the distant reservoirs of rock and ice, to nudge them out of their quiet orbits and send them falling toward the inner planets. And the answer, when scientists worked it out, turned out to involve the largest and most commanding members of our solar system, the giant planets, and a slow, majestic rearrangement of their orbits that reshaped everything around them. That is where we go next, to Jupiter, and the great gravitational architecture it helped to build. We tend to picture the solar system as a fixed and orderly thing. The sun at the center, the planets tracing their calm, patient circles around it, each one keeping to its own lane, the whole arrangement running like a great clock that has always looked more or less the way it looks now. It is a comforting picture, and for the planets as we see them today, it is largely accurate. Their orbits are stable and well behaved, and they have been for a very long time. But it was not always so. The order we see now is not the order the solar system was born with. It is, instead, the settled result of a far more turbulent youth, an ancient rearrangement in which the largest planets did not stay in the orbits where they formed, but moved, slowly and majestically, sweeping through the solar system and reshaping everything around them as they went. The tidy clock we admire tonight is the calm that followed a long and formative disturbance. The idea that the giant planets migrated came together in a set of computer models developed in the early 2000s by an international group of researchers, among them Alessandro Morbidelli, Harold Levison, and their colleagues. The work is often known collectively as the NICE model, named not for the quality of the idea, but for the city of Nice in southern France, where much of it was worked out, using careful simulations of how the young planets and the vast field of leftover debris would have tugged on one another over time. The Nice model offered a way to explain features of the solar system that had long been puzzling, and it did so by allowing the giant planets to move. To feel why this matters, it helps to sit with one gentle but powerful idea from orbital physics, the idea of resonance. When two orbiting bodies circle the Sun in a simple rhythm relative to each other, their gravitational nudges can add up in a coordinated way. Imagine one planet completing exactly 2 orbits in the time another completes 1. That is a 2-to-1 resonance. Because the timing repeats so cleanly, the smaller tugs between the two bodies fall in step, arriving at the same points again and again, reinforcing one another instead of averaging out. It is a little like pushing a child on a swing. A push at the right moment, in rhythm with the swing, builds up a large motion out of many small efforts. In just this way, orbital resonances can take the faint, repeated gravitational pulls between planets and amplify them into large, slow changes in their orbits over immense spans of time. According to the Nice model, something like this reshaped the early solar system. The giant planets in this picture did not begin in the orbits they hold now. They formed closer together, in a more crowded arrangement, surrounded by an enormous belt of icy and rocky leftover bodies further out, the material that never gathered into planets. Over long ages, the giant planets slowly exchanged tiny amounts of orbital energy with that surrounding debris and with one another. And at a certain point, the model suggests, 2 of the giant planets, most likely Jupiter and Saturn, drifted into a resonance with each other. When they did, the coordinated tugging of that resonance destabilized the whole outer arrangement. The giant planets shifted, some moving outward, and the great belt of leftover material was thrown into disorder. The consequences of that disruption spread across the entire solar system. As the giant planets rearranged themselves, their enormous combined gravity scattered the surrounding population of icy and rocky bodies in every direction. Some were flung far out into the distant frozen edges of the solar system, seeding the vast reservoirs of comets that still lie out there. Others were cast into the region between Mars and Jupiter, contributing to the asteroid belt. And a great many were sent falling inward, toward the Sun and the small rocky planets, including the Earth. This scattering of debris, set in motion by the migration of the giants, is exactly the kind of event that could send a long rain of material down onto the inner worlds, the very bombardment whose record we read in the face of the Moon in the last section. This is the sense in which the giant planets, and Jupiter above all, acted as the architects of the solar system. They did not simply sit in their orbits while the smaller worlds formed around them. By their sheer mass, and by the slow shifting of their positions, they governed where the leftover material of the solar system ended up. They decided, in effect, which debris would be exiled to the frozen outer dark, which would settle into the asteroid belt, and which would be sent inward toward the warm, rocky planets. The architecture we live inside, the stable arrangement of orbits and belts and reservoirs, was drawn in large part by the movement of the giants. As with the bombardment, it is worth being honest about what kind of knowledge this is. The Nice model is a powerful and successful piece of theory. It reproduces a surprising number of the solar system's features from a single unfolding story, and that success is why it is taken seriously. But it is a model, a mathematical reconstruction of events that happened billions of years ago and that no one observed. Its details depend on the starting conditions the researchers feed into their simulations, And those conditions are not known with certainty. So we hold it too, with a light grip. It is our best current picture of how the solar system rearranged itself, well supported and widely used, but a reconstruction rather than a witnessed fact. That is not a weakness. It is simply the honest status of a story pieced together from physics and evidence long after the event. What the Nice model gives us, for our purposes tonight, is the beginning of an answer to the question the moon left us with. The rain of debris that struck the early Earth was not random or unexplained. It was set in motion by the slow migration of the giant planets, whose shifting orbits stirred the distant reservoirs of rock and ice and sent a portion of them falling inward. The giants disturbed the water. Now we need to follow one giant in particular, and one especially dramatic journey it may have taken, to see how the water-rich rocks in particular, the dark carbonaceous bodies whose fingerprint matched our oceans, were swept out of the outer solar system and delivered to a small, dry planet near the Sun. Because Jupiter, it turns out, may have done more than nudge the debris from a distance. It may have gone traveling deep into the inner solar system and back out again, in a grand detour that carried Earth's water with it. To understand the journey Jupiter may have taken, we need to picture the young solar system not as the finished thing it is now, but as a work still very much in progress. The Sun had formed. The giant planets had gathered their great bulk out in the cold, beyond the snow line, where ice was plentiful and there was ample material to build with. But the inner region, where the small rocky worlds were slowly assembling, was still unsettled. The planets were not yet in their final places. Gas still lingered in the disk, and that lingering gas, it turns out, may have set the largest planet in motion. Here is the idea, developed and refined by a group of researchers, including Kevin Walsh and Alessandro Morbidelli, the same Morbidelli we met with the Nice model, in work published around 2011. It carries a wonderful name borrowed from sailing. They called it the Grand Tack. In sailing, to tack is to swing the boat through the wind, changing direction, turning a course that was heading one way so that it heads another. And that, the model proposes, is very nearly what Jupiter did. It sailed inward toward the Sun, then turned and sailed back out again. Let us walk through it slowly, because it is a genuinely surprising piece of history. In the Grand Tack picture, Jupiter did not simply form near its current orbit and stay there. While the disk of gas still surrounded the young Sun, that gas exerted a steady drag on Jupiter, and the giant planet began to spiral inward, drifting slowly toward the Sun across a long stretch of time. It migrated in through the region where the asteroid belt now lies, and kept going, moving inward until it reached a point not far from where Mars orbits today, roughly 1.5 times the Earth's distance from the Sun. A planet more than 300 times the mass of the Earth had wandered deep into the inner solar system, into territory we now think of as our own neighborhood. Then it turned, Saturn forming and migrating behind it, caught up and fell into a resonance with Jupiter, the two giants locking into that coordinated rhythm we spoke of in the last section. The gravitational partnership between them reversed the drift. Instead of continuing to spiral inward toward the Sun, Jupiter tacked, like a boat swinging through the wind, and began to migrate back outward, drawing Saturn along with it, until the two settled at last into something much closer to the orbits they hold today. Inward, then a turn, then back out. A grand detour by the largest planet in the solar system, traced across millions of years. Now, hold on to why any of this matters for the water in your body, because this is the heart of it. As Jupiter made its great journey inward and back out, Its immense gravity acted like an enormous rake dragging through the material of the solar system. On the way in, it disturbed and scattered the rocky bodies of the inner region. And crucially, on the way back out, as it crossed the zone between the rocky inner planets and the icy outer ones, it swept up a portion of the water-rich bodies that lived out there. The dark, carbonaceous, water-bearing rocks whose fingerprint we found matched our oceans, and it flung them inward. This is the mechanism the whole detective story has been building toward. Those water-rich rocks had formed out beyond the snow line, in the colder territory where ice could survive. Left to themselves, they would have stayed out there, far from the dry inner planets, and Earth might never have received them. But Jupiter's passage stirred that outer material and scattered a share of it inward, onto paths that crossed the orbits of the small rocky worlds. Over the long ages that followed, some of those scattered water-bearing bodies found their way down to the young Earth, delivering their locked-in water to a planet that had none of its own to spare. The dry inner solar system was seeded with water from further out, and Jupiter's grand detour was the hand that did the scattering. There is a quiet irony worth sitting with here. Jupiter is, by an enormous margin, the most powerful gravitational force in the solar system apart from the Sun itself. It is the great disruptor, capable of tearing comets apart and flinging bodies clear out of the solar system. We might easily think of it as a purely destructive presence. And yet, in this story, that same overwhelming gravity is very likely the reason Earth has oceans at all. The most disruptive planet in our system may have been the gentle deliverer of our water, not by intention, of course, but simply as a consequence of where it wandered and when. The force that destroys is the same force that provided. It is the kind of connection that the universe seems to make without any concern for how it looks to us. And there is a further thread of fortune woven through it, one that becomes clear only when you consider what might have happened otherwise. In the grand tack picture, it was Saturn's catching up and locking into resonance that turned Jupiter around. Without that turn, Jupiter's inward migration might have simply continued. The largest planet could have carried on spiraling toward the Sun, ploughing through the inner solar system, disrupting or destroying the very region where the small rocky planets, including Earth, were trying to form. The particular pairing of these two giants, the timing of Saturn's arrival, the resonance that reversed the drift at just the right distance, all of it had to fall into place for the inner solar system to survive intact and receive its water. Change the timing, and the story we are telling tonight might have no one in it to tell it. It is worth holding all of this lightly, in the same way we held the NICE model and the bombardment. The Grand Tack is a model, a reconstruction built from careful physics and simulation, not an event anyone watched unfold. It is elegant, and it explains several puzzles at once, including why Mars is so surprisingly small, which is one of the things that first motivated it. But it remains a proposed history, dependent on assumptions about the early disk that we cannot fully verify. What we can say is that it offers a coherent and much-studied answer to a real question: how water-rich rocks from the outer solar system ended up striking a dry inner planet, and that answer places the movement of the giant planets at the center of your own existence. So we now have a story with a shape to it. Earth formed dry. Water-bearing rocks formed further out, beyond the snow line. The migration of the giant planets, and Jupiter's grand detour in particular, scattered a portion of those rocks inward, where they fell, over long ages, onto the cooling Earth, and gave it the beginnings of an ocean. It is a satisfying account, but an account, however elegant, is not the same as proof. We have motive and we have mechanism. But a careful investigation wants something more solid than a good story. It wants a sample. It wants to reach out to one of these ancient water-bearing rocks, not one that fell to earth and sat in a field gathering contamination, but a pristine one, caught in the clean vacuum of space, and to measure its fingerprint directly. And that, remarkably, is exactly what one spacecraft set out to do. In December of 2014, a Japanese spacecraft named Hayabusa 2 left Earth on a long errand. Its destination was a small, dark, near-Earth asteroid called Ryugu, a body a little under a kilometer across, orbiting the Sun on a path that sometimes brings it into Earth's neighborhood. The name Ryugu comes from an old Japanese folktale, the palace of a dragon god beneath the sea, a place a fisherman visits and returns from carrying a mysterious box. It was a fitting name for the mission, because Hayabusa 2 was going to that dark world for one purpose above all. It was going to bring back a box. Ryugu is exactly the kind of object our investigation had been pointing toward. It is a carbonaceous asteroid, a C-type in the astronomers' classification, which places it in the same broad family as the Murchison meteorite from Section 5. These are the dark, primitive, carbon-rich bodies, the ones expected to carry water bound into their minerals, the very sort of rock the Grand Tack may have scattered inward toward the early Earth. But there was a crucial difference between studying Ryugu and studying Murchison. Murchison fell through Earth's atmosphere, landed in a field, and sat in our environment, where earthly water and earthly chemistry could seep into it and blur its original signature. Ryugu had never touched the Earth. If we could reach it and take a sample without contaminating it, we would be holding a piece of the early solar system, as clean as the day it formed. We would be reading a fingerprint that no earthly influence had ever smudged. That was the promise and the difficulty of the mission. It is one thing to observe an asteroid from a distance. It is another to travel hundreds of millions of kilometers, arrive at a body less than a kilometer wide, and gently take a piece of it. Hayabusa 2 reached Ryugu in the middle of 2018, after 3.5 years of quiet travel, and settled in to study it from close range. What it found was not a solid boulder, but a rubble pile, a loose heap of rock and dust and stone held together by its own faint gravity, its surface strewn with boulders and remarkably short of the smooth, flat places a spacecraft would prefer to touch. The team had to study the surface with great care to find anywhere at all safe enough to make contact. When the moment came, Hayabusa 2 descended toward the surface, touched it briefly, and collected material, both from the surface itself and, in a second operation, from a little beneath it, using a small impactor to expose fresher material that had been shielded from space weathering. Then it lifted away, sealed its precious cargo inside a return capsule, and began the long journey home. In December of 2020, 6 years after it had left, the capsule separated from the spacecraft, entered Earth's atmosphere, and came down by parachute into the quiet of the Australian outback in the desert of South Australia. Inside it were a few grams of Ryugu, dark grains of an asteroid, sealed and pristine, delivered to Earth without ever having been exposed to our air or our water. A piece of the ancient solar system had been carried home, clean. Then the real work began, in laboratories rather than in space. Scientists opened the sealed capsule under carefully controlled conditions and began to study the grains, and among the many questions they asked was the one our whole story has been circling. What is the deuterium to hydrogen ratio of the water bound inside Ryugu? What is this pristine asteroid's fingerprint, And how does it compare to the water in Earth's oceans? The answer closed the loop. The water held in Ryugu's minerals carried a deuterium to hydrogen ratio that sits close to the value of Earth's oceans, within the range that supports a carbonaceous asteroid origin for our water. This was not the wild mismatch we found at Comet 67P, where the water was 3 times too heavy. This was a fingerprint that belonged more or less to the same family as our seas. A pristine, uncontaminated sample, taken directly from a dark asteroid in space and returned without ever touching the Earth, was carrying water that looked like a close relative of the water in your body tonight. It is worth being careful and honest about what this does and does not prove, because that care is exactly what makes the conclusion trustworthy. A single asteroid, matched at the level of the fingerprint, does not by itself prove that asteroids like it delivered every drop of Earth's water. The match is a strong confirmation of a suspect, not a signed confession. But set it beside everything else we have gathered, and it carries real weight. We had the water-bearing meteorites that fell to Earth, like Murchison, whose fingerprint fit. We had the comets ruled out by Rosetta for carrying water too heavy. We had a mechanism, the migration of the giant planets and Jupiter's grand detour, capable of delivering exactly these carbonaceous bodies to the inner solar system. And now we had a pristine sample, fetched directly from space and free of any earthly contamination, confirming that a real carbonaceous asteroid carries water of very nearly the right kind. Each strand was suggestive on its own. Woven together, they make a genuinely strong case. That is the quiet satisfaction of this moment in the story. The master question we opened back in section 4, when we first learned to read the fingerprint, has found its answer. The water that fills Earth's oceans and moves through your cells as you rest here tonight was delivered in large part by the dark, humble, water-bearing rocks of the solar system, scattered inward long ago and matched at last by a sample carried home to an Australian desert. We had to travel hundreds of millions of kilometers to a rubble pile asteroid named for a dragon's undersea palace and bring back a few grams of dust to find the chemical near double of the water that comes out of your kitchen tap. The loop is closed. The most obvious suspect was cleared, the humbler one was confirmed, and the case, in its main outline, holds together. And yet, as satisfying as that resolution is, it is not quite the whole of the story. The honest truth, which the researchers themselves are careful to say, is that Earth's water almost certainly did not come from a single source. The fingerprint of our oceans is a kind of average, and an average can be made from more than one ingredient. There are threads still hanging loose. There is the question of how the oceans could carry the exact ratio they do. If the asteroid water alone is not a perfect match, there is water that seems to have come from an entirely different and unexpected place. And there is the deepest question of all, the one hidden in the title of tonight's journey, the possibility that some of this water is older than the sun itself. We have solved the main case. Now we go deeper into the subtler and stranger layers beneath it. And the next thread begins somewhere no one expected to find water at all. It begins with the sun. Of everything in the solar system, the sun seems the least likely place to look for water. It is a vast ball of glowing plasma, its surface roughly 5,500 degrees, its core a nuclear furnace hotter than we can easily imagine. Water cannot survive anywhere near it. If anything, the sun has spent the whole history of the solar system driving water away, as we saw at the very beginning, when its fierce young wind swept the last of the loose water vapor out of the inner disk. The sun is the great enemy of water, the source of the heat that kept the inner planets dry. And yet, In one of the more surprising turns in this whole story, the sun turns out to be a quiet maker of water as well. Not in its blazing interior, but in the thin stream of particles it constantly breathes out into space. That stream is the solar wind, and it never stops. Day and night, the sun pours out a steady flow of charged particles in every direction, and by far the most common of these particles is the humble proton, the bare nucleus of a hydrogen atom, a single positive charge stripped of its electron. These protons race outward across the solar system at hundreds of kilometers per second, washing over every planet, every moon, every drifting grain of dust in their path. Most of the time, we do not think of the solar wind as chemistry. We think of it, if at all, as the thing that lights up the auroras, or that spacecraft must be shielded against. But when that rain of protons meets the right kind of surface, something quietly remarkable can happen. To understand it, we need to know what those surfaces are made of. Out in the solar system, drifting in space, and coating the surfaces of asteroids, are countless tiny grains of silicate minerals, the same broad family of rock-forming minerals that make up so much of the planets. And silicate minerals are rich in oxygen, bound up inside their crystal structure. So picture the situation. You have grains full of oxygen, and you have a constant wind of hydrogen nuclei, of protons, streaming in from the sun and striking those grains. Hydrogen and oxygen. Those are, of course, exactly the two ingredients of water. What the solar wind delivers to these grains is a supply of the one ingredient the oxygen-rich rock was missing. When a fast-moving proton from the solar wind slams into the surface of a silicate grain, it buries itself a tiny distance into the material, and there, among the oxygen atoms of the mineral, it can bond. Proton by proton, hydrogen atom by hydrogen atom. Water begins to form in the outermost skin of the grain, a film only nanometers thick, built atom by atom out of the collision between sunlight's wind and ordinary rock. The sun, which drove the water away in the beginning, turns out to have been quietly manufacturing new water on the surface of every exposed grain in the solar system, all along. This is a beautiful idea, but ideas need evidence, and the evidence came from an earlier sample return mission, the one that gave Hayabusa 2 its name and its heritage. The original Hayabusa, launched by Japan in the early 2000s, visited a different near-Earth asteroid called Itokawa and returned tiny grains of it to Earth in 2010. Itokawa is a different type of asteroid from Ryugu, a stony S-type rather than a dark carbonaceous one, and its grains sat in collections for years. Then, in 2021, a team led by Luke Daly at the University of Glasgow examined those grains with an extraordinary technique called atom probe tomography, a method so precise it can map the position of individual atoms in the outermost few nanometers of a sample. Looking at the very skin of the Itokawa grains, exactly where the solar wind would have struck, they found water, and they found it in just the way the theory predicted, concentrated in the thin outer layer where the protons had implanted themselves. Here was direct evidence that the solar wind really does make water on the surfaces of asteroids. Now recall the fingerprint, because this is where the discovery joins our larger story in a way that is genuinely elegant. Solar wind water is made almost entirely from ordinary protons, from light hydrogen, because the sun's wind carries very little of the heavy twin, deuterium. So this solar-made water is unusually light. Its deuterium to hydrogen ratio is very low, far lower than the water in Earth's oceans. On its own, it does not match our seas at all. It is, if anything, too light, and that turns out to be exactly what the recipe needed. remember the puzzle we left hanging at the end of the last section. The water from carbonaceous asteroids like Ryugu was a close match to Earth's oceans, but the fit was not perfect. An Earth's ocean fingerprint is an average that could be built from more than one ingredient. Here, then, is a second ingredient with the opposite character. Asteroid clay water tends to run a little on the heavy side. Solar wind water is very light. Mix the two together in the right proportions. A large amount of the asteroid water blended with a smaller share of the light, solar-made water, and the heavy and the light average out. They can average out, in fact, to something very close to the exact ratio of Earth's oceans. The slightly too heavy and the very light combined land right where our seas sit. It is a lovely resolution to sit with in the quiet. The source of Earth's water was never going to be a single, tidy origin. It was a blend, a mixture of waters born in different ways and carrying different signatures that happened to combine into the particular fingerprint our oceans carry. And one of those ingredients was manufactured, atom by atom, by the very sun, whose heat and wind had done so much to keep the inner solar system dry. The great enemy of water was also, in its own small and patient way, one of its makers. The universe, once again, holds two opposite truths together without the slightest difficulty. We should hold the exact proportions of this blend lightly, as the researchers do. Precisely how much of Earth's water is solar-made, how much came from carbonaceous asteroids, how much from other sources, remains a genuinely open question, an area of active measurement and debate. What the Itokawa grains established is not a final accounting, but a real and previously unsuspected contributor. The sun made some of our water. How much, we are still working out. So the picture grows richer and a little stranger than the clean, single-source story we might have hoped for. And with the fingerprint puzzle eased, we can turn from where the water came from to when it arrived, and how quickly the young Earth actually became a water world. For a long time, the assumption was that oceans came late, long after the planet had cooled. But a single, almost unimaginably small grain of crystal, found in the hills of Western Australia, would tell a very different story about how early the first water may have gathered here. There is a range of low-weathered hills in the dry heart of Western Australia called the Jack Hills. They are not much to look at, ancient red ridges of rock worn down by an almost unthinkable stretch of time, baking under a hard sun in one of the older and quieter corners of the planet. A traveller passing through might see nothing remarkable in them at all, and yet these hills hold some of the oldest solid fragments of the earth that have ever been found, tiny survivors that have outlasted nearly everything else the planet ever made. To find them, you do not look at the hills themselves. You look at the grains washed out of them, and in particular at one extraordinary kind of crystal, a mineral called zircon. Zircon is one of nature's great timekeepers, and it earns that role by being almost stubbornly indestructible. It is a hard, durable mineral, chemically stable, resistant to heat and weathering in a way that few other minerals can match. A grain of zircon can survive being buried, uplifted, eroded out of its parent rock, tumbled down rivers, and locked into entirely new rock again and again across billions of years, and still preserve inside itself a faithful record of the moment it first crystallized. When a zircon forms, it also traps small amounts of radioactive atoms in its structure, which means it carries the same kind of built-in clock we met with the lunar rocks. By measuring how far those atoms have decayed, scientists can date a single zircon grain with remarkable precision. A speck of mineral you could lose on a fingertip can carry an accurate age reaching back to the earliest days of the world. In 2001, a team, including the geologist Simon Wilde, reported the age of a particular zircon grain from the Jack Hills, and the number was astonishing. The crystal had formed about 4.4 billion years ago. To feel the weight of that, recall that the Earth itself formed only around 4.54 billion years ago. This grain had crystallized within roughly 100 million years of the planet's birth, which, against the vast backdrop of geologic time, is very nearly the beginning. It is among the oldest fragments of the Earth ever dated, a genuine relic of the infant planet, somehow carried intact across almost the entire history of the world, to be picked out of the Australian dirt and read. But the age alone, remarkable as it is, was not the deepest part of the discovery. The real surprise was hidden in the chemistry of the crystal, in the particular atoms of oxygen it had trapped when it formed. And to understand what those atoms revealed, we need one more gentle idea about isotopes, the same kind of idea we used for hydrogen. Just as hydrogen comes in a light and a heavy version, so does oxygen. Most oxygen is the light kind, oxygen 16. A small fraction is heavier, oxygen 18, carrying a couple of extra neutrons. And just as with hydrogen, the balance between these two forms of oxygen is shifted by certain processes, and one of the most important of those processes is the interaction of rock with liquid water at relatively low temperatures. When water works on rock at the surface of a planet, weathering it, altering it, cycling through it, it tends to leave the resulting material enriched in the heavier oxygen 18. So the ratio of oxygen 18 to oxygen 16 locked inside a crystal can serve as a subtle signal of whether liquid water was present and active when the material that formed the crystal was made. When scientists measured the oxygen isotopes inside the ancient Jack Hills zircon, they found a signature that pointed toward exactly that, the involvement of liquid water. The oxygen locked in this 4.4 billion-year-old grain carried the mark of a world where liquid water was already interacting with rock at a relatively cool surface. In other words, the crystal was quietly testifying that the very early Earth was not the endless sea of glowing magma we might have pictured. Within roughly 100 million years of its formation, the planet already had a solid crust cool enough and liquid water present enough to leave this signature behind. This was a genuine shift in the picture. Scientists had generally assumed that Earth stayed a hellish molten world for a very long time, with oceans arriving much later, only once the planet had finally cooled and settled. The Jack Hills zircon pushed the arrival of liquid water dramatically earlier, to almost the beginning of the Earth story. It suggested that the planet cooled far more quickly than anyone had expected, developed a crust, and gathered liquid water at its surface, remarkably soon after it formed. The oceans, or at least the first standing water, may be nearly as old as the planet itself. It is worth pausing on the sheer improbability of how we know this. A single crystal, smaller than a grain of sand, formed in the first 100 million years of the Earth's existence. It survived the entire subsequent history of the planet. Every upheaval and erosion and remelting carried along and locked away and freed again, until it came to rest in the sediments of some quiet hills in Western Australia. And there, billions of years later, a human being picked it up, measured the atoms inside it, and read from them the news that the young Earth had water at its surface almost from the start. The planet kept a receipt from its own infancy, and we finally learned how to read it, and there is a quiet resonance here with everything that has come before. We have been building a picture of water arriving at the Earth, delivered by carbonaceous asteroids scattered inward, blended with a little water made by the sun's own wind. The Jack Hill's zircon tells us that this delivery, whatever its exact timing and sources, had already done enough of its work astonishingly early. By 4.4 billion years ago, there was liquid water here. The gathering of Earth's water was not a slow, late afterthought in the planet's history. It was there almost from the opening chapter, quietly present while the world was still very young. But water arriving early and water staying are two different things. It would be a comfort to imagine that once the first oceans gathered, they simply remained calm and continuous ever after. The truth is more turbulent and in its way more remarkable. The young Earth was still being struck by enormous bodies, some of them large enough to do something almost unthinkable to a young ocean. The seas of the early Earth, it seems, were not made only once. They may have been made and unmade and made again, boiled away into the sky and gathered back as rain, more than once in the planet's restless youth. That is the story we turn to next. We tend to think of the ocean as one of the most permanent things there is. It was here before us, it will be here after us, vast and steady and unchanging on any scale that matters to a human life. But steady is a word that belongs to human time. Stretch your view back into the deep past of the planet, into the first few 100 million years after it formed, and the ocean becomes something far less settled. In that distant youth, the sea was not a fixed and finished thing. It was still being assembled, still being tested, and more than once, it seems, still being destroyed and rebuilt. Part of the ocean's water arrived from outside, delivered by the water-bearing rocks we have followed all night. But another part came from within, breathed out of the planet itself. The early Earth was intensely hot inside, its interior a churning body of molten and semi-molten rock, and that molten interior held water, dissolved into it, locked into its minerals, mixed through the magma. As the young planet slowly cooled and its surface began to solidify, that trapped water was released, rising up and escaping into the atmosphere as vapor. This process, the venting of water and other gases out of a cooling, molten planet, is called magmatic degassing, and it was studied in careful detail by researchers including Hidenori Genda in work around the middle of the 2000s. Their models showed that degassing alone could have supplied a very large amount of water to the early surface, potentially enough to account for a substantial fraction of an ocean, rising as steam from the cooling rock below. So picture the early Earth wrapped not in the blue seas we know, but in a thick, heavy atmosphere of steam, water vapor pouring out of the solidifying crust and hanging in a dense, hot shroud around the whole planet. As the surface continued to cool, that steam could begin to condense, gathering into the first standing water, the beginnings of an ocean fed both by delivery from space and by the planet's own exhalation. This is the picture the Jack Hill's zircon supports, a world that had liquid water at its surface remarkably early. The ocean was being born from two directions at once, from the sky above and from the rock below. But the same era that was building the ocean was also capable of destroying it. This is where more recent work, including studies by the geologist Nadia Draben, and building on earlier modeling by researchers such as Norman Sleep, adds a startling chapter. The young Earth, as we saw when we looked at the Moon, was still being struck by large bodies, and some of those impactors were not modest stones, but genuine giants, objects tens or even hundreds of kilometers across. When a body that large strikes a planet, it delivers an almost inconceivable amount of energy. And one of the consequences of such an impact, the models suggest, is that it could deliver enough heat to boil the ocean. Sit with that image for a moment quietly, because it is a strange and enormous thing to picture. A single impact, large enough that the energy it released heated the atmosphere and the sea so severely that the ocean itself began to evaporate. Not a patch of it, but potentially the whole of it, lifted off the surface of the planet and turned to a global blanket of steam. The rock records that Draben and others have studied preserve traces of such colossal early impacts, and the modeling indicates that the largest of them may have been capable of vaporizing the oceans of the young Earth, turning the entire sea into a searing atmosphere of vapor that wrapped the planet in cloud. And then, slowly, it would have come back. A steam atmosphere cannot last. Held aloft by the heat of the impact, it would hang there for a time, a hot and heavy shroud kept from raining out by the runaway warmth of the aftermath. But heat radiates away into space. Over years, over centuries, over however long it took, the steam atmosphere would gradually cool. And as it cooled, the vapor would begin, once again, to condense, and it would rain. Not an ordinary rain, but a rain of almost unimaginable scale and duration. The entire vaporized ocean falling back out of the sky over a stretch of time that may have run to centuries, filling the low basins of the world all over again. The ocean that had been lifted into the sky would return to the ground, and the sea would be reborn. This may have happened more than once. In the restless youth of the planet, while the great bombardments still delivered occasional giants, the ocean may have been vaporized and reformed several times over, each cycle boiling the sea into the sky and then raining it patiently back down. The water we have been tracking did not simply arrive and settle into calm basins to wait for us. It went through fire. It was lifted whole into a scalding sky and returned as centuries of rain, perhaps again and again, before the planet finally quieted enough for the oceans to endure. There is something almost mythic in this, though every part of it comes from physics and the reading of ancient rock. The sea we know, the one that looks so permanent, was forged and unforged in the crucible of the early Earth, breathed out of molten rock, delivered from space, boiled into the heavens by titanic impacts, and rained back down over centuries, more than once, until at last it stayed. The water in your body carries that history in it. Every molecule of it may have been part of an ocean that was lifted into a global steam sky and fell again as an ages-long rain in the violent, formative youth of the world, long before there was anyone here to shelter from the storm. And we should hold the details of this loosely too, as we have with so much of tonight's story. Exactly how many times the early ocean was vaporized, exactly how large the impacts were, exactly how the water arriving from space balanced against the water breathed out of the mantle. These are matters of active research, refined with each new study of the ancient rock record. What is clear is the shape of it. The early ocean was dynamic, not static. It was made and unmade and made again, in a long, turbulent process that eventually settled into the steady seas we take for granted. We have now traced the water's origin and its early, tumultuous history on Earth. But there is one more layer beneath all of this, the deepest and quietest of all, the layer that gives tonight its title. We have found where much of the water came from, the carbonaceous asteroids and the sun's own wind. We have found how early it arrived, and how violently it was reshaped once it was here. What we have not yet asked is how old the water molecules themselves truly are, not how long they have been on Earth, but when and where they first formed. And the answer to that reaches back before the Earth, before the asteroids, before even the sun began to shine. We have spent the whole night tracing where Earth's water came from and how it arrived, But there is a question underneath all of that, one we have been circling since the very first sentence. Not where the water came from, but how old the water molecules themselves actually are. Not how long they have been on Earth, but when and where they first formed. And the answer, remarkably, is that a great deal of the water in your body is older than the Sun. It did not form in the solar system at all. It formed before the solar system existed, in the cold and the dark of interstellar space, and then survived the birth of our star to become part of the Earth and part of you. To understand how that is possible, we have to go back further than we have gone all night, to before there was a sun to speak of. Long before our star ignited, the material that would one day become the solar system existed as part of a vast cold cloud of gas and dust drifting in the galaxy. Astronomers call these giant molecular clouds, and they are among the coldest places in the universe, with temperatures only a little above absolute zero, hovering somewhere around 10 degrees on the Kelvin scale, which is more than 260 degrees below zero in the everyday Celsius we know. These clouds are enormous, spanning many light years, and they are the nurseries where new stars are born. Our Sun was born from one of them, and so was everything that orbits it. It is in exactly these cold clouds that water first forms, and it forms in a way that has nothing to do with any star. Scattered through the cloud are countless tiny grains of dust, and on the frigid surfaces of those grains, atoms drift down and stick. Oxygen atoms and hydrogen atoms wandering through the cloud settle onto a dust grain and meet, and in the profound cold they bond, building water molecule by molecule as a thin coating of ice on the surface of the grain. No warmth is needed for this, no sunlight, no planet, just the slow, patient chemistry of atoms meeting on cold dust in the dark. Across the immense stretches of time that these clouds endure, that quiet process coats the dust grains with mantles of water ice, so that the cloud, cold and starless as it is, becomes salted throughout with frozen water. So the water existed first as interstellar ice, formed in the dark before any star shone on it. And then, from a cloud like this, our solar system began to form. As we saw at the very beginning of tonight's journey, a region of the cloud collapsed under its own gravity, spinning into a disk, warming at the center where the sun would ignite. And here is the crucial question. When that collapse happened, when the cloud heated and churned and the sun caught fire, was the old interstellar water destroyed? Did the violence of the star's birth break apart those ancient ice mantles and reset the chemistry, so that all the water in the resulting solar system was made fresh, from scratch, in the new disk? For a long time, this was genuinely uncertain. It was possible, in principle, that the heat and turbulence of the collapse would have vaporized and scrambled the old water, erasing its interstellar heritage entirely. But the evidence, gathered by studying the chemical signatures of water across the solar system and by careful modeling, points the other way. It suggests that a significant portion of that ancient interstellar ice survived. The collapse was not uniformly violent. In the colder, outer reaches of the forming disk, far from the heat of the growing sun, the old ice could persist, carried into the new solar system largely intact, inherited rather than remade. A 2023 study from the University of Copenhagen was among the work examining how Earth's water breaks down into different components, with different origins, and the picture that emerges from this line of research is that a substantial fraction of Earth's water, by some estimates a large share of it, is inherited interstellar ice, older than the sun itself. Let that settle slowly, the way the night has been settling around you. Some of the water in your body did not begin in an asteroid or in the sun's wind, or anywhere in the solar system at all. It began on a grain of dust in a cold cloud between the stars, before there was a sun, before there was an Earth, before there was any of this. Those water molecules formed in the dark, drifted through the collapse that made our star, rode into the forming solar system, gathered into the bodies that eventually struck the young Earth, and passed through the long history of the planet, all the way down to the glass you might have set beside your bed tonight. When you drink water, some of what you are drinking is genuinely ancient beyond the age of the sun, a survivor of the interstellar dark carried down to you across more than 4.5 billion years. We should hold the exact fraction lightly, as always. Precisely how much of Earth's water is inherited interstellar ice, as opposed to water processed and reformed within the solar nebula, is an open and actively studied question, and different studies give somewhat different answers. But the essential finding is robust and remarkable. It is not all inherited, and it is not none. A real and meaningful portion of the water on Earth, and therefore a real portion of the water in you, predates the sun. The title we began with, that the water in your body is 4.5 billion years old, turns out, for some of that water, to be an understatement. Part of it is older still. There is a particular kind of quiet that comes with this realization, and it is a good place to rest. All night we have been reaching further and further back, from the water in your veins, to the oceans, to the asteroids, to the migrating giant planets, to the sun's own wind, and now to the cold clouds between the stars that came before the sun was ever lit. We have followed the water almost to the beginning of its story, and what we have found is that the water is not a local thing, not an earthly thing, not even a solar thing. It is older and more widely traveled than the star we orbit. It is, in the truest sense, a piece of the galaxy, resting for a while inside you. And that raises one last, gentle widening of the view. If water forms so readily in the cold dark between the stars, on grains of dust with no star required, then it should not be rare. It should be everywhere. The water in you would not be a strange local accident, but one small instance of something the universe does constantly, wherever hydrogen meets oxygen in the cold. Before we come home, all the way home, to the body at rest in the quiet room, we are going to take one slow look outward at how much water there truly is, first in our own solar system, and then out among the stars themselves. For most of human history, we imagine the Earth as the water world, singular and alone, a blue jewel in a dry, dead solar system, the one place where water gathered and life could take hold, surrounded by barren rock and empty cold. It was a natural thing to believe. Every other world we could see looked parched, or frozen, or scorched, and none of them showed the open blue that makes the Earth so recognizable. But the missions of the last few decades have quietly overturned that picture, one world at a time. The solar system, it turns out, is not dry at all. It is soaked in water. The water is simply hidden, tucked beneath ice and rock and the surfaces of distant moons, waiting in the dark. Earth is not the exception. In many ways, Earth is just the world where the water happens to sit on the outside. Begin close to home, with Mars, the neighbor we visited early tonight, the world that lost its surface water long ago. Even there, the water is not entirely gone. In 2018, using a radar instrument called MARSIS aboard the European Mars Express orbiter, scientists reported bright radar reflections beneath the ice of the Martian South Polar Cap. Reflections of the kind you might expect from a body of liquid water buried deep below the surface. The interpretation has been debated ever since, with some researchers suggesting the signals might come from certain clays or particular kinds of rock rather than liquid water, and the question is not fully settled. But the possibility remains genuinely open that even cold, dry Mars still holds pockets of liquid water hidden far beneath its frozen south, the last quiet remnants of the seas it once had. Now travel outward, past the asteroid belt, to the great moons of Jupiter, and here the water becomes astonishing. Europa, one of the 4 large moons Galileo first saw through his telescope, is wrapped in a shell of ice. And beneath that ice, the evidence strongly indicates, lies a global ocean of liquid salt water, a sea that covers the entire moon and is kept liquid not by the distant sun, but by the constant flexing of Jupiter's gravity, which kneads the moon's interior and warms it from within. This hidden ocean, sealed beneath its icy crust, is thought to contain more water than all of Earth's oceans combined. A moon smaller than our own holds, in its dark interior sea, more liquid water than the entire surface of the Earth. Europa is not alone among Jupiter's moons. Ganymede, the largest moon in the whole solar system, larger even than the planet Mercury, is thought to hold a deep, briny ocean sandwiched between layers of ice in its interior. Callisto, another of the great Galilean moons, appears to carry a subsurface ocean of its own. These are not small quantities of water. In their bulk composition, the icy moons of the outer solar system can be nearly half water by mass, whole worlds built substantially out of the very substance we set out tonight to trace. Travel further still, out to Saturn, and to one of the loveliest discoveries in all of modern planetary science. Enceladus is a small, brilliantly white moon of Saturn, only about 500 kilometers across, and for a long time there was little reason to think it remarkable. Then the Cassini spacecraft, which orbited Saturn for 13 years, discovered something extraordinary near the moon's south pole. From a set of fractures in the ice, nicknamed the Tiger Stripes, Enceladus is venting great plumes of water vapor and ice grains directly into space, geysers erupting from a hidden ocean beneath its frozen shell. And Cassini did something wonderful with those plumes. It flew straight through them, sampling the spray, and found not only water but salts and organic molecules, tasting the chemistry of a hidden alien ocean without ever having to land. A tiny moon at the far edge of the ringed planet system is quietly spraying its buried sea into the sunlight, and a spacecraft from Earth flew through the mist and drank it in. The list goes on, gently, world after world. Titan, Saturn's great hazy moon, is thought to hold a subsurface water ocean beneath its surface, even as its cold surface hosts lakes and seas of liquid methane and other hydrocarbons, sampled in part by the Cassini mission and its Huygens lander. Far out at the edge of the classical solar system, even Pluto, that small and distant world, shows signs in the data from the New Horizons flyby of a possible ocean of liquid water buried deep beneath its frozen crust. And closer in a different key entirely, the Messenger mission found water ice tucked into permanently shadowed craters at the poles of Mercury, the planet nearest the Sun, where the crater floors never see sunlight, and the cold endures even there. Water at the innermost edge of the solar system, and water at its farthest reaches, and water on world after world in between. Step back and take in the whole picture, slowly, the way you might take in a wide night sky. The pattern is unmistakable. Water is not the rare and precious exception we once imagined it to be. It is one of the most common substances in the solar system, present nearly everywhere we have learned to look. It fills the hidden oceans of the outer moons, hides beneath polar ice, lingers in shadowed craters, and coats the icy bodies of the distant dark. If anything, it is the dry, sunlit surface of the Earth that is unusual, the rare place where the water sits out in the open, warmed enough to pool on the surface under a breathable sky, rather than sealed away beneath a shell of ice. The rest of the solar system keeps its water hidden. Earth simply wears it on the outside. There is a deep comfort in this when you rest with it. The water in you is not a lonely and improbable thing, clinging to the one wet rock in a dead and empty system. It is a small portion of something the solar system holds in abundance, a substance so common that it fills the interiors of distant moons and gathers into oceans larger than our own beneath miles of ice. You are made largely of the most ordinary material there is, the same water that soaks the whole neighborhood of worlds around the sun. Far from being alone, the water in you belongs to a family that spans the entire solar system. And that family does not stop at the edge of the sun's domain. If water is this common here, gathered into the moons and worlds of a single ordinary star, then the natural question is whether it is common out there too, among the countless other stars of the galaxy. The answer, gathered by our newest and most powerful telescopes, is that it is. Water is not just a feature of our solar system. It appears to be one of the most common things in the universe, forming wherever the ingredients meet, in the disks around newborn stars, and in the atmospheres of worlds orbiting suns unimaginably far away. That is the last outward step we will take tonight, before we come home, all the way home, to the water at rest inside you. Why should water be so common? Before we look out at the wider galaxy, it is worth pausing on that question, because the answer is written into the basic chemistry of the cosmos, and it explains everything we are about to see. Water is made of hydrogen and oxygen, and those two elements are not chosen at random from a long list. Hydrogen is the single most abundant element in the entire universe, the first to form after the birth of the cosmos, the raw material from which nearly everything else was later built. And oxygen, forged in the hearts of stars, is the most abundant of the heavier elements, the most common of the atoms that stars manufacture and scatter when they die. So the two ingredients of water are, quite simply, among the most plentiful atoms there are. When you combine the most abundant element in the universe with the most abundant of the heavy elements, you get water. It is almost inevitable. Water is not a rare accident. It is close to a natural default of cosmic chemistry, the thing the universe makes whenever hydrogen meets oxygen in the cold. This is why, when we point our best instruments outward, we keep finding it. Consider the disks around newborn stars, the protoplanetary disks like the one our own solar system formed from, the flat, spinning plates of gas and dust, where new planets are being assembled right now around other suns. The James Webb Space Telescope, the most powerful space telescope ever built, has been able to study these disks in extraordinary detail, reading the chemistry of their gas and dust by the light that passes through them and the infrared glow they give off. And in disk after disk, Webb finds water. It finds water ice coating the dust grains in the cold outer regions, and it finds water vapor in the warmer inner zones where rocky planets would form. The same process we imagined at the very start of tonight's journey, water freezing onto dust in a young disk, is not a story we reconstructed only for our own system. It is something we can watch happening right now around other stars, in the light Webb gathers from across the galaxy. Other worlds are being seeded with water before our eyes. Now go further, to the planets themselves, the worlds already formed and orbiting distant stars, the exoplanets. Studying them is one of the great achievements of modern astronomy, because these worlds are so far away and so faint, lost in the glare of the stars they circle. And yet we have learned to read their atmospheres. When a planet passes in front of its star, from our point of view, a little of the star's light filters through the planet's atmosphere on its way to us, and the gases in that atmosphere leave their fingerprints in the light, each one absorbing its own particular colors. By reading those fingerprints, astronomers can tell what an exoplanet's air is made of, across distances of tens or hundreds of light years. And again, among those fingerprints, they find water. One world in particular has drawn a great deal of quiet attention. It is called K2-18b, a planet substantially larger than Earth, orbiting a small, cool red star. What makes it interesting is that its orbit places it in what astronomers call the habitable zone, the range of distances from a star where temperatures might allow liquid water to exist. And when the Hubble Space Telescope, and later the James Webb, studied the light passing through K2-18b's atmosphere, they found the signature of water vapor along with other molecules. A world larger than our own, orbiting a distant star, carries water in its air, in the very zone where a star's warmth might allow that water to gather. We cannot say what lies beneath that atmosphere, and much about the planet remains uncertain and debated. But the water is there, detectable across the immense gulf between us, a reminder that the substance filling your cells tonight is present in the skies of worlds we will almost certainly never visit. And K2-18b is far from the only one. Water vapor has now been detected in the atmospheres of many exoplanets, including some of the strangest worlds ever found, the great scorching gas giants that orbit extremely close to their stars, so close that their years last only days and their upper atmospheres glow with heat. Even there, in atmospheres hot enough to melt rock, telescopes have picked out the signature of water molecules, water vapor woven into the searing air of worlds utterly unlike our own. From cold disks around infant stars to the blistering skies of these close orbiting giants, across every kind of environment we have learned to examine, the same simple molecule keeps appearing. Water is everywhere the universe allows it to be, and the universe allows it almost everywhere. Let that widen the view gently as the night draws toward its close. The water in your body is not a local curiosity, not even a solar one. It is one small instance of something woven through the entire galaxy. The disks around distant newborn stars are freezing water onto their dust at this very moment, seeding planets we will never see. The atmospheres of far-off worlds carry water vapor in their skies. The same molecule that moves through your blood and cushions your brain is being made and gathered and carried across the whole vast reach of the cosmos by the same simple chemistry that made yours. You are not made of some rare and special substance found only here. You are made, in large part, of one of the most common and most widely scattered materials in all of existence. There is a profound and quiet comfort in that thought, and it is exactly the note to carry us home. All night we have travelled outward and backward, from the water in your veins to the oceans, to the asteroids and the migrating giant planets, to the sun's own wind, to the cold clouds that came before the sun, and now to the disks and worlds of distant stars. We have followed the water as far out as we can go. And everywhere we have looked, we have found the same thing, the same molecule, the same ancient and abundant substance, present across the solar system and across the galaxy alike. The water in you connects you not just to the earth, and not just to the sun, but to the whole of the cosmos, to every place water gathers, which is to say very nearly everywhere. And now, at last, after this long journey out to the edge of what we can see, it is time to come home, all the way home, back across the light years, back through the solar system, back to this planet, to this room, to the quiet rise and fall of your own breathing in the dark. Because the most remarkable place in this entire story, the place where all of it finally arrives, is not some distant disk or hidden ocean or ancient cloud. It is here, it is you, and that is where we will rest. So let us come home now, all the way home, and rest here for a while. You are lying in your room, in the quiet and the dark. Your breathing has slowed. The day has loosened its hold, and somewhere in the steady rhythm of your body, in the blood moving gently through you, in the fluid that cushions your brain, in the water held inside every one of your cells, there is a substance that has traveled further and waited longer than almost anything you could name. We have followed it across the whole of the night and the whole of the cosmos. Now, at the end, it is simply here, inside you, doing the quiet work of keeping you alive as you drift toward sleep. Think, one last time and very gently, of where it has been. Every atom of hydrogen in the water inside you formed at the very beginning of everything, in the first minutes after the birth of the universe, some 13.5 billion years ago. Before there were stars, before there were galaxies, the young cosmos made hydrogen, and that hydrogen has been part of the universe ever since. The lighter half of every water molecule in your body is that old. It is nearly as old as time itself. The oxygen came later, and from somewhere just as remarkable. Oxygen is not made in the calm of empty space. It is forged in the hearts of stars, built up in the nuclear furnaces of massive suns over the course of their lives, and then released into the galaxy when those stars reach their ends and scatter their contents outward. Every oxygen atom in the water inside you was made inside a star that lived and died long before the sun was born. The heavier half of every water molecule in your body was cooked in stellar fire and cast out into the dark when its star was finished. And then, in the cold between the stars, in one of those vast and frigid molecular clouds, the hydrogen and the oxygen met. On the surface of a tiny grain of dust, in a cold deeper than anything on Earth, they bonded into water and froze there as a thin skin of ice. That happened before the sun existed. Some of the water in you was already water, already formed, already ancient, before there was a solar system for it to belong to. It drifted in the dark as interstellar ice, waiting, in a universe that had not yet made our star. Then the cloud collapsed, and the sun caught fire, and the water was carried into the newborn solar system. Some of it froze onto the dark, carbonaceous rocks that gathered beyond the snow line. And when the giant planets shifted in their slow, majestic migrations, when Jupiter made its grand detour inward and back out again, a portion of those water-bearing rocks was scattered toward the young, dry, molten Earth. Over long ages, they fell, and their water joined the water breathed out of the cooling planet itself, and the first oceans gathered. Those oceans were boiled into the sky by titanic impacts and rained patiently back down, perhaps more than once, until at last they stayed. And from that point on, the same water has been moving through the world in an unbroken stream ever since. That is the part worth resting on at the very end. The water did not simply arrive and stop. It has been moving continuously for 4.5 billion years. It has been ocean and cloud and rain. It has been rivers and glaciers and morning fog. It has passed through the bodies of every living thing that has ever existed on this planet, through ancient forests and vanished seas, through creatures that swam in waters we will never see, through the great, slow cycles of the world, again and again and again. The water in you tonight is not new. It has been here the whole time, taking one form and then another. And now, for a little while, it has taken the form of you. It is on loan, as we said at the very beginning. You are holding it for a time, and one day you will pass it on, back into the rivers and the rain and the great shared water of the earth, where it will go on to be part of other living things long after you, just as it was part of countless others before you. You are not the owner of this water. You are its keeper for a while. One more stop on a journey that began before the sun and will continue long after tonight. And so, when you drink a glass of water, or feel your own slow breathing in the dark, you are in quiet contact with the deepest history there is. You are touching the birth of the universe, in the hydrogen. You are touching the life and death of ancient stars, in the oxygen. You are touching the cold clouds between the suns, and the migration of the giant planets, and the young Earth's first patient rains. All of it is here, gathered into the warm and living shape of you, resting in this room, breathing in the dark. More than half of what you are is this ancient, traveled, borrowed water, and it has carried the whole story of the cosmos quietly inside you all along. There is nothing you need to do with any of this now. Nothing to hold on to, nothing to remember. You can simply let it be true, the way the water in you simply is. Let your body rest into the support beneath you. Let your breathing stay slow and easy. And let yourself feel, just for a moment before you drift off, that you are not a small and separate thing in a cold and empty universe. You are made of the universe. You are made of its oldest water, gathered from the stars and the dark and the deep history of this world, and held together tonight in the shape of someone at rest. The water in you is 4.5 billion years old, and some of it is older still. It has crossed the galaxy and survived the birth of the sun, and moved through every ocean this world has ever had, only to arrive gently here in you on this quiet night. So rest now. The water has waited a very long time to be you. It is in no hurry, and neither are you. Let it carry you the way it always has, down into a deep and peaceful sleep. Sleep well. We will drift together again another night.